So you probably think empty space is, well, empty, right? But what if it's not? What if even a perfect vacuum at the coldest temperature possible is actually buzzing with a hidden energy? And get this, from that nothingness, a real physical force can actually emerge.
Okay, so let's dive right in. Just look at this gecko. I mean, it's just strolling across the ceiling, totally defying gravity. How on earth does it do that? It's not suction cups, and it's not some sticky goo on its feet. Nope. It's holding on with a force that comes from the very fabric of reality.
And here's the crazy part. This isn't just some clever trick of evolution. The exact same principle that lets this gecko do its thing, it also messes with our most advanced, tiniest machines. And it throws a massive wrench into how we understand the whole universe. So what's the connection? What's this invisible thread that ties a gecko's feet to the fate of the cosmos?
Well, to find that answer, we've got to leave our everyday world behind and dive headfirst into the strange and kind of wonderful world of quantum physics.
So that secret grip, it's all thanks to something called van der Waals forces. These are just these tiny, super short-range attractions between atoms. But here's the thing. Those forces, they're really just a symptom of something much, much deeper. An energy that's literally bubbling up out of empty space. Okay, so to really get a handle on this force, we need to talk about energy. But I'm not talking about the energy of, a moving car or something. I'm talking about the energy baked into empty space itself.
And this brings us to the key idea, zero-point energy. See, in our big everyday world, we think you can stop something completely, right? Remove all this energy. But down at the quantum level, no way. That's impossible. There's always this minimum amount of energy, a baseline that you can never, ever get rid of. So even in a perfect vacuum, space itself is just buzzing with these things called quantum fluctuations. Here's a great way to think about it, and this analogy comes from the physics fan at the University of Illinois. Imagine a tiny mass on a spring. Now, thanks to the Heisenberg uncertainty principle, you can't know its exact position and its exact motion at the same time. It's just not possible. That means it can never be perfectly still. It's always got to be jiggling just a little bit. And that tiny minimum jiggle, that is its zero-point energy.
And this is a perfect example of how science really happens. The physicist Hendrik Casimir was totally stumped by these weird forces between molecules. So he's talking to the legendary Niels Bohr, and Bohr just kind of mumbles something about zero-point energy. Just an off-the-cuff remark. But that one little comment was the spark that lit a fire and led to a whole new idea. Okay, so how do we get from a constant background jiggle to a real, actual force you can feel? Well, Casimir's brilliant thought experiment shows us exactly how it works. All right, picture this. You have two perfectly flat metal plates, and they're super close together in a total vacuum. Now remember, that vacuum is teeming with all sorts of quantum fluctuations, every possible wavelength you can imagine. But, and this is the key part, between those two plates, only some of those wavelengths can fit. It's like a guitar string, only certain notes can resonate. This means a ton of other fluctuations are kicked out from the space between the plates, even though they're still buzzing around on the outside. So what does that do? It creates a pressure imbalance. You've got more energy, more fluctuations pushing on the outside of the plates than on the inside. The result? A net force pushes the plates together. They are literally being squeezed by empty space. And that, right there, is the Casimir effect, a real, measurable force from nothing.
So this isn't just some weird idea on a chalkboard. This force has real, tangible effects in our world. But that's also where things get a little weird, because it's led to a lot of myths and misunderstandings.
Take, for example, engineers who design these tiny microscopic machines called MEMS. For them, the Casimir force is a huge headache. I mean, at that tiny scale, the force is actually strong enough to make little parts stick together, permanently. They even have a name for it, stiction. So yeah, this is a very real problem they have to engineer around. But this is also where you get the myth of free energy machines, right? The idea that we can just pull endless power out of the vacuum. But the science on this is really, really clear. Zero-point energy is the ground state. It's the absolute lowest energy level possible. Think about it. You can't get energy from something that's already hit rock bottom. There's nothing left to take. The folks at the physics van in Illinois said it best. Trying to get energy from the zero-point field, well, it would mean leaving something with less energy than the lowest possible energy state. It just doesn't make sense. It's a total contradiction, kind of like trying to dig a hole that's deeper than the bottom. Okay, so no free lunch. We got it. But this is where the story gets really, truly mind-bending. Because what happens when you stop thinking about tiny plates and start thinking about the entire universe?
You know, when the physicist Wolfgang Pauli first heard about zero-point energy, he thought it was absolute nonsense. And why? Because he instantly saw the huge cosmic problem. See, Einstein taught us that all energy has gravity. So if empty space is just packed with all this energy, it should be bending and warping spacetime on a scale we can't even imagine. Just how big of an effect are we talking about? Well, physicists did the math. They calculated how much energy should be in the vacuum according to quantum theory. Then they looked at what we actually observe, the dark energy that's making the universe expand. And the numbers didn't just disagree. They were off by, well, this much. That's a 1 with 120 zeros after it. It's a number so big, it's hard to even wrap your head around.
I'm not kidding. This has been called the worst prediction in the history of physics. Think about it. Our two best theories of the universe, quantum mechanics and general relativity, they give us completely catastrophically different answers for the energy of empty space. And that gigantic gap, that's what's known as the cosmological constant problem. And it is, without a doubt, one of the biggest unsolved mysteries in all of science. So let's just recap for a second. We're left with this absolutely staggering thought. The very same force that lets a gecko casually walk up a wall also points to a massive, fundamental breakdown in how we understand the entire universe. So which is it? Is this energy from nothing the key that will unlock a new theory of everything? Or is it proof that our best ideas about how the universe works are just profoundly wrong? That is the question that keeps physicists up at night.